we stop at the work done by the weight given by this formula. Work, we use capital U to represent work. Work equal to negative W delta Y. Right? Work equal to force and displacement. Yeah. Work is done when the force and the displacement, they are in the same direction. Yeah. Okay. Force and displacement. So for gravity force, you will have a negative force because it's acting down, and your reference axis Y is positive going up. That's why you get a negative work when you consider weight in your question. Today we look at one more devices that we always use in engineering, which is a spring force. Now, you learn in your static module when you learn about spring. Spring, you have a spring stiffness, right? So the force acting on the spring when you press on it, how you find the spring force? You take the spring constant times the distance traveled by the spring, right? The spring either contract or expand, right? Same with this when we talk about spring. So let's say you are given a spring setup like this. So this is unstretched position, x equal 0. Right? So you have spring, and then you have a force on here, this particle here. You have a K, S, and ds. ds means the change of position. And you can calculate the force on the particles itself with the work, right? From this diagram, you can calculate du means the work, the small changes of work done by the spring equal minus fx dx. Again, what is work? Work is the work is the dot product of your force and displacement. Both of them must be in the same direction. Then the products of the dot products, it will give you work. So spring is negative ds. Okay, in this case, this is the datum, right? So what does the work done by the displacement here? Right. So you can expand your fx. Fx equal to kx. K is a spring constant. S is the distance that you pull the spring. Okay. Right. Why you have a negative sign here? There's a statement here. You have a negative because of the direction. Yeah. Because of the direction. The force is going this way. However, the spring is going positive this way. Yeah. So if the particle displacement from S1 to S2, the work that you done, because this equation is a partial differential, which is you use the D mean very small changes of work or small effort of work. This is ds means very small distance travel by the force, right? Force and the distance, you create work. So you want to find the total work done by the system, you need to use integration this side and integration on the right hand side. So left hand side, when you integrate du, you get u. When you integrate right hand side from s, from first position to second position, you can write in this form. Integration of S1 to S2 fs dot ds. In this case, it's a dot product. Again, what is work? Work is you take the force, multiply by the same direction of your displacement. Force and displacement must be in the same direction. Then work can be done. Okay, so this is equation, derivation equation for spring. For spring. So you substitute the kx inside there, you get the work done by the spring. Okay, later we have some example on this one. The concept is still the same. How you get work? Work equal to force times ds. Right? So force equal to ks, spring constant times the distance that you pull from the spring. There's a typo error here. I forget about the negative sign here. There should be a negative sign here. Okay, typo error. Let me correct it in my slides. Okay, there's a negative sign here. Okay. All right. Okay, error was corrected. So when you have you do the integration. Okay, you do the integration, you will get minus, because your k is a constant, you can either pull the constant out or it can remain. So when you integrate kx ds, actually you add something on the top here. S power 1, you add 1. 1 plus 1, you get 2 divided by 2. That's why you get this 1 over 2 ks square 2 minus the first one. Okay, so try to polish your integration skill for this module. So I'm not going to explain how to do integration in this module. So here you get this one. All right. So what does this equation means? You can always imagine this one in a Cartesian graph. Force as on the our y-axis, x as your displacement. So you're finding the differences between the two dots on the line. Right? So this one is the area under the graph between S1 and S2. So this is a green area that defined by this equation. Yeah. All right. So this is the work done by the spring. So sometimes you will be confused when you need to use a positive, when you need to use a negative for spring. So I summarize this signage issue in these slides. So you observe the direction. So if the direction of the spring force and the direction of displacement, they are the same, what happened to the notation? If they are opposite, then what happened to the notation? For the spring, you observe two things. One is the direction of the force, spring force. One is the direction of the displacement of the particles. Okay, so if both they are same direction, then you get work positive. If they are opposite direction, you get negative. Okay, just memorize the red color bracket, the information inside here. Or we just repeating what we learned in the previous class. Force and displacement, they must be the same direction. So if they are moving in the same direction, you get the positive work. If either of them are opposite, let's say your force is another way, so the combination of this force and this displacement will give you negative work. Okay, so this is for your checking, or your when you do your test later, you check your answer. All right, the work done by the spring, whether it's positive or negative. You look at the motion of the spring and the force. Okay, let's look at one example that relate to this statement. Right, so look at example 1. Right, you have this question in your handout, in your tutorial handouts, right? Okay, we have a spring system like this. So we have a spring system slanted at 30 degree. Okay, there's a plane of sliding. Okay, the angle between the horizon and the sliding plate here is 30 degree. You have a spring attached to the bottom, and on the top of the spring there is a cube there, there's a weight there, and you're given the spring constant K equal to something. Of course in test this one will change, but K will be given. You're given the distance. Okay, this cube, what happened to this cube? This cube, this spring, how this works means that this cube was compressed. Okay, this force was compressed and let go. So you get a displacement of 2 meters, and there's a change of y altitudes or y distance. Okay, try to extract information from the statement here. You are given the mass of the block. You have 10 kilo. Rest on a smooth incline, so you will start from the rest. If the spring is originally stretched 0.5 meter, what does it mean? If the spring original is stretched, means it's stretched to the back, 0.5 meter. Stretch 0.5 meter is stretched like that, in this position. Determine the total work done by all the force acting on the block when a horizontal force 400 Newton push the block up to the plane S equal to 2 meter. So initially you start from here, and then there is a force acting on the cube 400. You push the block up. Okay, so there are lots of action over here. One is by the force, one is by the spring. Okay, so when you read chapter 3 question, kinetics question, try to observe what you have in the question. If a spring, is it a spring? Is it a force? Is it a gravity? Just because before we look at this example, we look at work done by a force in a straight line, in the curvilinear line. We look at weight, how weight work done by the weight or gravitational acceleration, and also work done by spring. So we combine what we learned in one example here. So how do we solve this kind of question? So always start with a free body diagram of the block. So you draw a square and have the orientation of the square like the question. Put in the axis like usual. So free body diagram, start with the body and regenerate the orientation of the object as in the question. So here you have a few axes. So you know that the first force you put in the free body diagram is your weight. So you put your weight in the center going down. Right, W equal to mg. These are the first steps when you solve chapter 3 question. You need free body diagram. Yeah, free body diagram. You draw the object shape. If the object is too complex for you to draw, you just can use any dot or any square or standard shape to represent that object. Okay. Then after that, you draw the axis. You draw the direction of the force. You put in the force, the weight, you know, always pointing down from the center. W equal to mg. And you know that there's an angle of 30 degrees from the surface. Right? So this is a normal. If you draw a normal 90 degree from the surface here, this is a slanted surface. You draw a 90 degree, you get this axis, and your force is moving down with 30 degree because the plate is moving 30 degree. For this module, since chapter 2, you will see we'll always add one normal force so that this object always stick on the surface. Or you see any scenario that the object have contact with any surface, you need to add a normal force below the object. Okay, normal force always pointing up. Next, you add in a vertical force that given in a question. Vertical force, sorry, horizontal force, 400 Newton into the free body diagram. Put in the angle also with 30 degree. Any question so far for the free body diagram? Any question?
So far, no, sir.
Good, yeah? All right. Stop me if you're not able to understand the free body diagram, yeah? I only need to highlight is that normally in tests, this force will be, some of you will forget about this normal force. Just take note in your revision notes there. Don't forget this one, it's important. Next, we look at derivation of force. We look at work done by the force. Yeah, we have a few mechanism here. Force, we have a force, we have gravity, we have spring. So we will have three kind of work here. So we look at the force first. So this force and force previously when we introduced this chapter, force you have two motion. One is on the curvilinear, one in the straight line. So we will use the work done by the straight line equation. So if your force P moving in a straight line, we will use U equal to force cos theta sine 2 minus sine 1, or it just means that the work done by the force is same direction with your displacement. So what you do, you can either change your force parallel to the displacement, or you can move the displacement change parallel to the force. But my recommendation, always align your forces component to the surface that you are moving. That's why in this equation, I write force cos theta, meaning I use this component. You know that this is a force. Force you can expand. Sorry, my finger orientation. You can expand into two vector like that, two force like that. One pointing down, one moving up. Okay, you can expand this force into two forces like that. One pointing down, one moving along the axis. You know that the component 90 degree to the displacement do not generate force, right? We mentioned before. Force displacement, the angle from 0 up to 98.99 degree, you still generating positive work. But the force and displacement become 90 degree. There is no work done because cos 90 is 0. And if you increase the angle from 90 to, another direction, you get negative work. Okay? So this is the equation that you use. From force, you expand into two directions. Okay, two directions like that. My thumb do not generate any work because 90 degree to the surface. My finger, this one, going up is generating work because this finger here, my P in the finger direction, is parallel to your displacement and it's generating work. So you use P cos the theta multiplied by the change of displacement, you get the work done by the force. Substitute the value. So the work done by the P force, that's why I write capital U as a work, sub P to represent that it is done by the by the force of the P, equal 400 Newton cos 30 multiplied by 2 meter, because the original position of the spring, because you stretch the spring from here and then you let go, your cube is going to move out. Okay, so this is the equation we use when substitute the value. Okay, try to observe the distance that we use is from the starting point until the end point. We use 2 meter. In the question, we use 2 meter. We do not use this one or we do not use this one. Why? Because our force and displacement must be in the same direction. Then you're creating work. Okay? You press your calculator, you get one answer. The unit is in joule. If you don't know how to write joule, you can put in Newton meter. Same unit. Joule equal to 1 joule equal to 1 Newton meter. Force is in Newton, displacement is in meter. So the resulting unit is Newton meter. Or when it come to work, standard unit is joule. But if your answer is Newton meter, I still give you correct. Okay. Reminder, answer without unit in exam, we will have discount 50% from the full mark. Yeah. Meaning this one, if the answer is 2 mark, you forget to put in the unit, you only get 1 point for the answer. Okay, take note on that. Yeah. In your calculation, I can still close one eye. I can still not looking for the unit in your calculation. But when it comes to final answer or important answer, you have to give the unit. Don't forget about the unit. Any question so far for the work done by the force? Everyone good?
Yeah, so far okay, sir.
All right.
I got a question for
Yeah,
the
go ahead. Go ahead. Yeah, go ahead. What is your question?
So the free diagram, I'm confused with the direction of the force of the spring.
Oh, here, this one.
Yes, sir.
Okay. Okay. Good question. My solution, my way of solving this kind of question, when I draw free body diagram, I imagine myself as that object. You imagine yourself as that object. What do you feel if okay, this direction, sometimes it can be going in or it can be pulling out. in the spring. You agree, right? So this spring, this arrow, it can be sometimes going in or it can be going out. Because this case, if you pull this one from this location before start, the spring is pointing into your bodies, right? If you are this body, the spring is pointing in. So your spring force actually is pointing in. But what happened if the spring reach this area, reach this S here? You feel that the spring is pulling you, right? When you reach this position. Correct? Now, for this arrow, okay, for this arrow, normally you look at the end position. Free body diagram, you always consider what happened at the end location. In this case, what is the maximum displacement, or what is the question asked you to focus on? He asked you to focus on the distance at 2 meters, which means initially you pull 0.5. You feel that the spring is punching in your body. The force initially should going this way. But the question asks you to focus at the location of 2 meters. You imagine you are the block and you will release from this location as you reach this position. You will feel that the force is pulling from your back, right? If you are the cube or you're facing the spring here, you will feel that the spring is actually pulling you, right? So the spring the direction is going here. Anyway, in exam, if you put the wrong not wrong but if you put in going up, no issue, because later your answer will tell you the spring force will be negative. No issue one this one. If in the exam, if this one you put going up, in your calculation here, if your force is going up, right? Later when I talk about spring later. Well, now this equation is on the force P first. Later when talk about spring, then you will see what happen if you do the wrong, or not wrong but you put in the opposite direction. Okay, at the moment, I think you agree with my explanation on the direction. Sometimes it can go in, sometimes it can pull out. It depends on location. But why do I draw it pull out? Because I follow the question. The question asked me to focus on 2 meter. So what happened when I at 2 meter? I feel that the spring actually pulling me. So I have a force pulling from this point. This diagram I draw based on location number 2 here and not 1. Okay?
Understand.
Okay, now let's move on spring. Apologize for not hiding this one. But let's look at spring. We have done with the P force work already. Now we go for spring. So initially, again, it was 2.5. And then final position here is you have to know the final distance traveled by the spring. The final position actually is 2.5. Okay, the final position, actually the total distance traveled from the initial position here is 2.5 and then move to 2 meter. The final displacement done by the object is 2.5. Initial position is 0.5. But anyway, when you calculate force, right, I will calculate work is force and the total displacement done. So basically it's 2 meter. So it's from the starting point to the end point. But this is only important when you are told to plot graph. Right? For info, I won't ask you to draw graph. So this is just information about the displacement, about the position. Right? Okay, so just now we have come up with the spring equation just now. Work done by the spring, U2 equal to negative the second position minus first position. Okay. Okay, why negative in this work here? It is because if you look at this diagram, where does the spring work? It work go back and then go up, right? So there's a marking here. Negative because the force and displacement are opposite on each other. So in this case, when we calculate, you get a negative work done by the spring. Because in it, the original is here, you load the spring. You load the spring by pulling the spring 0.5 to the back. This is the work you done on the spring. After you release that one is another thing already. Important is what have you done to the spring. Okay, what have you done to the spring? Okay, you can see you pull out and then you go up. Huh? So for spring that acting in this behavior, you pull, you let go. You actually calculating S2 here. You are using 2.5 because that is the last position. S1 here, you are using this position, which is you already stretch 0.5. You do the calculation, you get negative. Negative means that the force and displacement actually different direction. Okay, we get the spring work already. Okay, maybe I'll give you some time to look at the slides. Okay. Can and we can see why negative because initial position is here, so you pull back. When you load the when you charge up the energy for the spring, you will get negative sign. That is how I memorize lah. When you charge up the spring, you get a negative. Okay, because in this section, the positive direction is for the spring is this direction, but the spring move that way. So the spring force and the displacement is opposite direction. Right? Or you can imagine that the force pressing on the spring that you load the spring earlier is opposite with the displacement done by the spring. That's why you get a negative. Okay. We have two load already, two work already. By the P and by the spring, both in joule, yeah? Both in joule unit or capital J, or you can write in Newton meter also correct. Next, we look at gravity. Weight going down. Okay, going down. Why negative? Why negative? Why negative? Because our positive axis is always going up. So you use the equation, right? UW, let's see, okay. U equal to minus W delta Y. All right. So your W here, you can either, okay, when you do work, right, you always align your force and displacement together. Then only can generate work. So here, you can either move your sine 30 to the displacement, or you can move your sine 30 to the work, to the force. Same thing. Meaning you align your gravitational, this is your displacement direction. So again, you can split your gravitational force into two, I don't know how to place my finger, but you have two forces you can split from 30-degree here. So you can split into this direction and also this direction, right? What happens if you split in this direction? You know that this direction is perpendicular to the displacement direction, is 90-degree. So when you have 90-degree force and the displacement, there's no work done. So there's one more forces contributing to the work. It is in this direction. And remember, what is the direction of the force and the displacement? This direction going down. The object is moving up. That's why there's a negative sign there in your gravitational force. So you get, for gravitational work, UW equal to negative force sine theta, the multiply by the displacement. You get 90. Is it correct? Yeah, correct. 98.1. Because sine 30 is half. Half, take up 2, you get 1, you get 98.1 joule. Any question for the weight, for the gravitational force, or the weight done by the work done by the weight? Good. Stop me if you're not able to do. We have done P spring weight. There's one more force, which is your normal force here. Normal force also one of the component here. However, normal force is always 90-degree to the surface. Again, normal force is a force. However, the force, when the force is 90-degree to the displacement, force 90-degree to displacement, it doesn't do work. So there's a zero work done by the normal force. Okay, so work done by the normal force is 0. Sometimes this is the free mark. Don't miss out if you have a normal force. This will cost you 1 to 2 marks. Free. No equation, no calculation needed. Because this force always 90-degree to the contact surface. Always get 0. So 2 mark, 2 mark, 2 mark, 2 mark, 8 marks here. You have 2 mark, 3 mark here. Okay. And of course, if you forget about the unit, 8 marks become 4 marks. 8 marks, you can score 8 marks, but you forget about the J in your answer. The marks for your answer only 4 marks. You can see how serious it can affect your total marks at the end. So unit is very important. So total work, you add all these numbers together. You have positive, you have negative sign. Okay, you'll get one number. U total equal to 505 joule. This is just a reference number for you to check. Try to learn the strategy of solving question. What have we do? We look at a question, we develop free body diagram, we input all the forces there. All right. And for the spring especially, I will recommend you always consider the last position where it lasts. Then you imagine whether the spring is is punching in or pulling out. That is how I do my question. Okay, I always imagine I am that object and what happened to my connection between my body and the spring. Okay. All right. We have done with the work equation. Okay, let's stop here for a short break. Let me stop the recording.